12,800 years ago, the Atlantic conveyor collapsed. Greenland cooled by 10 degrees Celsius inside of decades. Europe froze. Sea ice spread south across an ocean that had only just thawed. The system stayed broken for 1,300 years. We know this because it is written into ice cores, ocean sediments, and pollen records. We have always known the AMOC could fail. What we did not know until 2026 was whether it was failing right now. A new study from Utrecht University just answered that question. They built a model fine enough to see the mechanism. They matched it against 31 years of satellite data. The Atlantic conveyor is already in stage 1 of collapse. Stay with me on this one, because the signal has been sitting in front of us for 3 decades, and what we are starting to understand is far worse than we thought. Drop a comment with the part of this that you wish more people understood. Hit subscribe so you don't miss the next signal we learn how to read. Now let's break this down. For nearly 2 decades, scientists who studied the Atlantic Ocean had a problem they could not solve. They could measure how fast the Atlantic conveyor was weakening. They could not measure how close it was to collapsing. Those are different questions. A car can be slowing down for hours without being anywhere near a stop sign. A car can also be coasting along at a perfectly normal speed, with an empty tank about to die on the highway. Knowing the speed is not the same as knowing the distance. For nearly 2 decades, the field had a speedometer. It needed a fuel gauge, and in 2026, a small team at a Dutch university just built one. They did it on a supercomputer the size of a building, with a simulation so detailed that running it on a normal laptop would take 14 million years. They forced the model with the exact kind of freshwater that is currently pouring out of Greenland. They watched what happened to the Gulf Stream as that water accumulated, and what they saw was not a slow, gentle slide into a warmer future. What they saw was a system with 2 stages, a long, quiet drift that lasts roughly 400 years. And then, at the end of that drift, a 2-year hinge. A sudden, catastrophic lurch where the conveyor falls off its pin and the entire Atlantic stops working. That 2-stage signature had never been documented in any climate model before, and once they had found it in the simulation, they went looking for it in the real ocean. They examined 31 years of continuous satellite data. They examined 61 years of subsurface temperature records. They wanted to know whether the slow drift of stage 1 was something the real Atlantic was doing right now. The answer came back from 2 completely independent data streams. Yes. The Gulf Stream has drifted approximately 53 kilometers north since 1993. Statistically significant, confirmed in altimetry, confirmed in temperature. The signature is real. The drift is real, and it matches the model's stage 1 trajectory almost exactly. That is the headline. The Atlantic Ocean is not at risk of entering stage 1 of a collapse trajectory at some point in the future. According to the new study and 30 years of satellite data, it is already there. Stop and sit with that for a second. The conveyor that keeps northern Europe habitable. The current that moves more energy every second than human civilization uses every year. The system that, when it failed 12,800 years ago, plunged Greenland into a 10-degree freeze inside of a few decades. That system has now been measured to be in the first stage of a collapse trajectory, not approaching it, in it. The team that ran the simulation did not say the sky was falling. They are careful scientists, and they were careful in their language. What they said was more unsettling than that. They said the fuel gauge they had built was now reading, and the needle was not on full. The research was led by René van Westen and Henk Dijkstra at the Institute for Marine and Atmospheric Research at Utrecht University in the Netherlands. They built a global ocean simulation at a 10-kilometer grid resolution, 10 times finer than the 100-kilometer grid that has been the standard in climate science for decades. The model required roughly 6 months of continuous runtime on Snellius, which is the Dutch national supercomputer. Snellius performs about 14 quadrillion calculations every second. 14 quadrillion. That is a 14 followed by 15 zeros. The same simulation, run on a typical laptop, would take approximately 14 million years. To put that in context, 14 million years ago, our ancestors had not split from the line that produced chimpanzees. So when you hear that this simulation existed at all, the right reaction is not, oh, another climate model. The right reaction is, somebody just spent 6 months of one of the most powerful computers in Europe to look at the Atlantic Ocean in a way that has never been done before. And what they saw is what this video is about. There is a tendency, when a story like this lands, to assume the result must be either exaggerated or so technical that a normal viewer cannot evaluate it. I want to push back on both of those instincts right at the front of this video. The Utrecht study is technical, yes. It is a 6-month supercomputer simulation interpreted by professional oceanographers. You and I are not going to verify the math at home, but the structure of the result is something a normal person can hold in their head, and the empirical confirmation, the 53 kilometers of measured drift, is not a model output. It is a number from satellite data that anyone with access to public archives can plot themselves. That is the part that makes this story different from most climate tipping point headlines. It is not a prediction. It is a measurement, attached to a mechanism, by a model fine enough to see what older models could not see. And the rest of this video is going to walk you through, slowly and carefully, exactly why that combination matters. To understand why this finding matters, you have to understand why nobody had ever seen the two-stage signature before. The reason is almost embarrassingly simple. Until 2026, no climate model had been run at a resolution fine enough to see it. Standard climate models, the ones that have been used by the field for 30 years, use grid squares of about 100 kilometers on a side. That sounds reasonable until you realize what it actually means. The Gulf Stream itself is about 150 kilometers wide. At 100 kilometer resolution, the Gulf Stream is 1 grid square wide, maybe 2. The whole current, the most important river in the ocean, compressed down to 1 or 2 pixels. At that resolution, the Gulf Stream is not a current. It is a smear, a blurry suggestion of warm water heading north. You cannot see where exactly it sits. You cannot see where exactly it bends. You certainly cannot see what happens underneath it. And what happens underneath, it turns out to be the entire story. The Atlantic conveyor has a return leg. After the warm surface water reaches the North Atlantic and sinks off the Norwegian coast, it does not just disappear. It flows back south along the seafloor, 2 miles down, as a separate deep current called the Deep Western Boundary Current. That current moves at a few centimeters per second. It hugs the continental slope of North America, all the way down through Cape Hatteras, past the Bahamas, and eventually out into the South Atlantic toward Antarctica. At 100 kilometer resolution, that deep current is completely invisible. The grid is just too coarse. The current is a thin, slow ribbon of cold water tucked against the underwater wall of the continent. And at 100 kilometers per pixel, you simply cannot resolve a thin, slow ribbon. It does not exist in the simulation. The Utrecht team's 10-kilometer grid is fine enough. At 10 kilometers, the Gulf Stream looks like a Gulf Stream. You can see where it sits along the American coast. You can see where it detaches from the continental shelf near Cape Hatteras. You can see where it meanders out into the open Atlantic. And critically, you can see the deep western boundary current sliding underneath it, 2 miles down, doing whatever it is that the deep current does. And what the deep current does, it turns out, is everything. The pinning interaction between the surface Gulf Stream and the deep western boundary current is the mechanism that holds the entire Atlantic conveyor in place. Once you can see it, you can see how it fails. Once you can see how it fails, the two-stage signature falls right out of the data. Until you can see it, the whole system looks like a slow, smooth weakening. The exact same data, looked at through a finer lens, tells a completely different story. That is the part that should make you uncomfortable. Not that scientists missed something exotic. They were looking at the right ocean. They had the right data. They had the right physics. They were just looking at it through a lens that was too blurry to see the mechanism. Once the lens got sharper, the mechanism became obvious. And the moment the mechanism became obvious, so did the fact that we were already inside it. So let's talk about what the deep western boundary current actually does. Imagine the Atlantic conveyor as a giant, planet-scale loop. Warm water enters the loop in the Gulf of Mexico. Wind pushes it north along the United States East Coast as the Gulf Stream. It curves out into the open Atlantic, releases its heat into the air above it, and eventually arrives in the high North Atlantic, near Greenland and Norway, where it has cooled enough and become salty enough that it is now denser than the water around it. So it sinks. It plunges down into the deep ocean and starts flowing south along the seafloor, 2 miles down, all the way to Antarctica, where it eventually upwells, warms up, and works its way back into the surface flow. One full circuit takes about 1,000 years. So far, so good. That is the high school version of the AMOC, and it is correct as far as it goes. What it leaves out is the rotational physics. The deep current does not just flow placidly along the seafloor. It rotates as it flows, because everything that flows on the surface of a rotating planet rotates. The Coriolis effect on a current that, deep, moving, that slowly, generates a torque, a spinning force. And when that deep current passes underneath the point where the Gulf Stream detaches from the American continental shelf, that torque acts on the surface current overhead. It pins the Gulf Stream in place. It holds it against the slope. It anchors the detachment point near Cape Hatteras and prevents the Gulf Stream from wandering north. As long as the deep current is strong, the pin is strong, and the Gulf Stream stays anchored. This is the part that had been described in older oceanographic literature, but had never been captured in a climate model. The pinning interaction, the torquey coupling between the surface flow and the deep return flow. It is a real physical effect. It just lives in a piece of the ocean that 100-kilometer grids cannot see. Now think about what happens as the conveyor weakens. As the AMOC slows down, the deep return flow slows down. As the deep return flow slows down, the rotational torque on the surface current weakens. As the torque weakens, the pin loosens. The Gulf Stream is no longer held quite as firmly against the continental slope. It starts to drift, slowly, slightly, not enough to look dramatic, not enough to look like anything other than a small, persistent northward shift. That is stage 1. That slow drift is the signature of a pin that is loosening but has not failed. The model says that drift continues for about 400 years. And then, when the pin finally goes, the Gulf Stream snaps. 219 kilometers north in 2 years. That is stage 2. And within about 25 years of that snap, the deep current no longer supports the surface flow at all. The conveyor collapses. The Atlantic conveyor is not held together by some abstract, statistical climate balance. It is held together by a specific, physical, rotational pin. That pin can be measured. The Utrecht study built the first model fine enough to see it. The next question, the one that should now be obvious, is whether you can see the pin loosening in real-world data. The answer is yes, and that is where things get really uncomfortable. The most important number in the entire Utrecht study is not a model output. It is a measurement. The Gulf Stream has drifted approximately 53 kilometers north since 1993. Let me be precise about what that means and where it comes from, because this is the part of the story that should land hardest. There are two completely independent ways of measuring the position of the Gulf Stream from space. The first is satellite altimetry. Satellites called Topex Poseidon, launched in 1992, and the Jason series, which has been operating continuously since 2001, measure the height of the sea surface to within a few centimeters. A current like the Gulf Stream produces a small but measurable bump in the sea surface because the rotating water lifts the ocean slightly higher on one side than the other. You can track that bump. You can see where it sits, and you can watch where it moves over decades. The continuous altimetry record now spans from 1993 through 2024, 31 years. And across those 31 years, the Gulf Stream's surface signature has shifted, slowly and steadily, approximately 53 kilometers to the north. That is one record. Here is the second record. Beginning in 1965, oceanographers started deploying instruments that measure subsurface temperature. They drop down into the ocean from ships, from buoys, from autonomous floats, and they record the temperature profile of the water from surface down to several kilometers. The Gulf Stream, being a warm surface current, leaves a characteristic warm signature in those profiles. When the Gulf Stream is overhead, you measure warmer water at depth. When the Gulf Stream moves, the warm signature moves with it. The subsurface temperature record now spans 6 decades. Independently, with no input from satellites, that record shows the same thing. The Gulf Stream has shifted north by approximately the same amount across 3 decades of satellite data. It crossed 6 decades of subsurface measurements. Both signals statistically significant. Both signals showing the same direction, the same magnitude, the same timing. That is not coincidence. That is empirical confirmation of an underlying physical change. And here is the part that should make you sit up straight. That 53 kilometers exactly matches the Utrecht model's stage 1 signature. The model says the Gulf Stream drifts northward by about 133 kilometers over the full 400-year duration of stage 1. 53 kilometers is about 40% of that total. We are not at the start of stage 1. We are not at the end. We are somewhere inside it. The model cannot yet tell us how far inside. The drift rate alone in isolation does not give us a position on the timeline. Stage 1 in the simulation runs at one rate. Stage 1 in the real ocean could be running faster or slower than that, because the real ocean is being forced by Greenland melt, plus surface warming, plus atmospheric shifts, plus Arctic sea ice loss, all simultaneously. The Utrecht simulation was a clean baseline, with one forcing. The real Atlantic is processing several at once, so we cannot read the exact position, but we can read the fact that we are inside the trajectory. And this is the part that should genuinely make a careful viewer uncomfortable, the part I want you to really sit with. The signal was sitting in publicly available satellite data for 31 years. Researchers were collecting it continuously. The instruments were on the satellites. The data was on servers. Anyone with the right access and the right tools could have looked at it and said, hey, the Gulf Stream is drifting. Some did. They noticed. They published. But nobody could yet say what it meant. Was the drift important? Was it just noise from one of the dozens of ocean oscillations that come and go on decadal timescales? Was it a transient response to some short-term forcing that would reverse itself? Nobody could say with confidence, because there was no mechanism to attach the drift to. It was a curiosity. What the Utrecht study did in 2026 was attach the drift to a mechanism, the deep western boundary current pin. Once you had the pin, the drift became legible. Once the drift became legible, it was no longer a curiosity. It was a stage 1 collapse precursor, and it had been sitting in the data for 3 decades. That is the part that should haunt you. Not that we missed something exotic. We were looking at the right data. We could not yet read it. Once we could, the signal was obvious. Until we could, the signal was just a slow, slightly puzzling northward shift in a current that everyone agreed was probably weakening anyway. The pin was loosening. We saw it loosening. We did not know it was a pin. Think about what that means for everything else we are currently measuring. There are dozens of similar long-running observational records sitting on public servers right now. Ocean temperature time series, ice mass balance records, soil moisture data, atmospheric methane concentrations, permafrost depth measurements. Every one of those records contains signals. Some of those signals are noise, some of them are normal cycles, and some of them, almost certainly, are the slow approach of mechanisms we have not yet identified. The Atlantic conveyor's first stage of collapse spent at least 31 years sitting on satellite servers as a faintly anomalous northward drift before anyone could read it as the loosening of a rotational pin. That timeline is not unusual. It is probably typical. The mechanisms in complex Earth systems are not easy to identify. They require the right model resolution, the right physical insight, and the right alignment of empirical data. Most of the time, all three pieces do not arrive at once. Most of the time, you have data without mechanism, or mechanism without data, or both with no model fine enough to bridge them. The Utrecht study is what happens when all three pieces arrive at the same time, and the result is one of the most consequential climate findings of the decade. There are almost certainly other findings of similar consequence still hidden in similar records, sitting there, waiting for the right model to make them legible. That is a structural feature of how Earth system science works, and it is the part of the Utrecht story that will most likely apply to other findings in the next decade. Let me back up for a minute and talk about what the AMOC actually is, because if you have not held in your head exactly how big the system is, the rest of this video is going to land soft. The Atlantic Meridional Overturning Circulation, the AMOC, the Atlantic Conveyor, whatever you want to call it, is the planet-scale ocean current that transports approximately 1 petawatt of thermal energy northward across the Atlantic Ocean. 1 petawatt. That is 1 quadrillion watts of continuous heat transport. The number is hard to feel, so let me anchor it. 1 petawatt is approximately 50 times the total energy consumption of all of human civilization. Every second, continuously, for thousands of years. Every car you have ever driven, every furnace in every building in every country, every server farm, every airplane, every factory, all of it, totaled, multiplied by 50, running constantly with no off button. That is what the Atlantic Conveyor moves, not the energy. The energy is something else again. That is just a comparison, so you understand the scale. The conveyor begins in the Gulf of Mexico, where shallow tropical water sits at around 27 degrees Celsius. Wind stress drives that warm water northward along the United States East Coast. It accelerates through the Straits of Florida, picks up speed past North Carolina, and emerges into the open Atlantic at about 2 to 4 miles per hour. By the time it is fully developed, the Gulf Stream is moving approximately 80 million cubic meters of water every second across a current about 150 kilometers wide. 80 million cubic meters per second. The total flow of every river on Earth, combined, all at once, is about 1 million cubic meters per second. The Gulf Stream alone on the surface is moving 80 times that. As the warm water travels north, it does what warm water does. It loses heat to the cooler air above it. The air, warmed by the water, blows east across the Atlantic toward Europe. And that, more or less, is why London is not Siberia. Britain sits at the same latitude as Hudson Bay in Canada, and parts of Siberia in Russia. Hudson Bay freezes solid every winter. Parts of Siberia drop below -40 Celsius regularly. London does not, because London sits downwind of an ocean that is being continuously bathed in tropical heat by the Gulf Stream. Norway is at the same latitude as the southern tip of Greenland. The Norwegian coast is habitable, with cities and farms and ports. The southern tip of Greenland is a glacier. Without the AMOC carrying tropical heat north, average winter temperatures across northern Europe would drop by approximately 10 degrees Celsius. London winter lows would be near -20. Scandinavia would become tundra, colder than modern Siberia. Growing seasons across northern Europe would simply stop functioning at the scale required to feed the population. When the warm water finally reaches the area off the Norwegian coast, it has cooled enough and lost enough freshwater through evaporation that it has become salty enough to grow denser than the water around it, and it sinks. The water plunges into the deep ocean and begins flowing southward along the seafloor, 2 miles down, as the deep western boundary current. That is the same current you heard about earlier, the one that pins the Gulf Stream in place. It moves at a few centimeters per second. A single water molecule that enters the deep flow off the Norwegian coast takes approximately 1,000 years to complete the full circuit and return to the surface near Antarctica. 1,000 years. The conveyor is enormous. It is slow. It is continuous. And it has been running on the same self-reinforcing feedback loop for thousands of years, since the last ice age ended. Feedback loops are stable until they are not. That is the structural lesson of the Utrecht study. What threatens the AMOC is the freshwater that is now pouring into the North Atlantic from the Greenland ice sheet. Cold water is denser than warm water. Salty water is denser than fresh water. The AMOC's deep water sinking depends on a precise density contrast between the cooled North Atlantic water and the surrounding ocean. As Greenland melts, cold fresh water enters that exact region of ocean, dilutes the salinity of the cooled Gulf Stream water, and reduces the density contrast that drives the entire conveyor. The cooled water still tries to sink, but it sinks with reduced force. It does not reach as deep. It does not move as quickly. The whole system loses energy. Greenland is currently losing ice faster than at any point in recorded human history. Satellite gravimetry from the GRACE and GRACE follow-on missions has been measuring the ice loss continuously for over 20 years. The trend has been accelerating, not stabilizing. Every cubic kilometer of meltwater that enters the North Atlantic is a small additional weight on the conveyor's structural integrity. And the Utrecht model used Greenland melt as its idealized forcing. Greenland melt and nothing else. The real Atlantic is processing Greenland melt plus surface ocean warming plus atmospheric circulation shifts plus changes in summer Arctic sea ice, all at the same time. The combined effect is not yet fully established. The real-world Stage 1 duration could be substantially shorter than 400 years, or it could be longer. We do not yet know. There is one more piece of the conveyor's physics that is worth sitting with before we leave this section. The Atlantic conveyor is not a closed system. It is connected to the global ocean circulation through the Southern Ocean, the Indian Ocean, and the Pacific. Heat that the AMOC moves north in the Atlantic is heat that does not move north in some other current, or it is heat that is replenished by warmer subsurface flow from the south. The conveyor is not a single isolated current. It is the Atlantic arm of a planet-wide circulation system that has been called the global thermohaline circulation. The thermohaline part of that name refers to the two ingredients that drive the whole loop. Thermal, meaning temperature, haline, meaning salinity. Together, those two ingredients control the density of seawater, and density is what drives the deep flow. Heat the surface, and it rises. Cool it, and it sinks. Add fresh water, and it floats. Remove fresh water through evaporation, and it sinks. Every part of the global ocean has its own temperature salinity profile, and the system as a whole arranges itself into a vertical and horizontal pattern that has been roughly stable for the last several thousand years. What is happening now is that one corner of that pattern, the North Atlantic Deep Water Formation region near the Norwegian coast, is being aggressively forced by Greenland freshwater into a configuration that resists deep water formation. The cooling is still happening. The salinity contrast is not. And without the salinity contrast, the sinking part of the conveyor weakens, which weakens the rotational pin, which is exactly the chain of events that the Utrecht study just described. The mechanism is not separate from the physics. It is the physics, made legible at a resolution that older models could not provide. Now here's the part of the story that should change how you think about all of this. The AMOC has collapsed before, not in a model, in the actual past, in the actual ocean, with consequences we can measure today in ice cores and ocean sediments. Approximately 12,800 years ago, near the end of the last ice age, the climate of the northern hemisphere was warming. Glaciers were retreating. Massive lakes of meltwater had accumulated along the edges of the receding Laurentide ice sheet, which once covered most of what is now Canada. One of those lakes, called Lake Agassiz, eventually grew so large that it covered a chunk of what is now Manitoba and the northern United States. The lake was held in place by the remaining ice sheet to its north. When the ice sheet retreated past a critical point, the dam gave way. The exact pathway has been the subject of decades of research, and the current best understanding is that the floodwaters drained primarily through the Mackenzie River system in northwestern Canada into the Arctic Ocean. From there, fresh water spread south across the surface of the subpolar North Atlantic like a cap, lighter than the salt water beneath it, spreading, diluting, cutting off the density contrast that drives the conveyor. The AMOC slowed dramatically, or it stopped entirely. The exact magnitude is still debated. What is not debated is what happened next. The climate of the northern hemisphere snapped back toward glacial conditions within decades. Greenland ice cores show temperature drops of approximately 10 degrees Celsius across a span of decades, and possibly within just a few years. Europe cooled by 2 to 6 degrees. Sea ice spread southward across the North Atlantic, swallowing coastlines that had only recently emerged from the last full glaciation. The episode lasted approximately 1,300 years. It is called the Younger Dryas, named for a small Arctic flower whose pollen suddenly appeared in European sediment cores from that period, indicating tundra conditions where temperate forests had been moving in. The Younger Dryas is the closest thing the geological record has to a controlled experiment in AMOC failure. The trigger was fresh water, the same kind of fresh water that Greenland is delivering today. The mechanism is not hypothetical. It happened. Once. We know it happened because we can read the ice. We can read the sediments. We can read the pollen. There is no model required. The collapse left a receipt, and the receipt has been sitting in the geological record for 12,000 years. And there is one more piece of the Younger Dryas record that is genuinely structural, that I want you to hold on to. When the Younger Dryas ended, it did not end gradually. The AMOC restarted in a single, rapid transition over a few decades. The temperature record in the Greenland ice cores shows a near vertical line on the warming side. The system did not slide back into operation. It snapped back. That is a clue about how the AMOC actually works. It is not a smoothly variable system that can sit at any speed between full speed and zero. It has two stable modes, running and not running, with a narrow, unstable corridor between them. You either operate in the running mode or you operate in the not running mode. If you fall off one mode, you do not slowly return to it. You either stay in the failure state for as long as the forcing persists, or you snap to the other mode when the forcing finally relaxes. Climate scientists call that property bistability. The system has two stable states, and it sits in one or the other, and it transitions between them through a narrow, unstable region, like a marble in a bowl with two cups, balanced briefly on the ridge between them. Approximately 50% of the freshwater hosing experiments that have been published in the climate modeling literature show the AMOC failing to recover after collapse, even after freshwater input stops entirely. Half the time, the system has hysteresis. Once the conveyor breaks, restoring it requires re-establishing the density contrast that drives it. And on civilizationally relevant timescales, that may simply not be possible. Stage 2 of the Utrecht model is not a phase the conveyor passes through and exits. It is a state it enters and stays in. So here is the receipt, plain and simple. The mechanism that the Utrecht study just identified, the deep western boundary current pinning the surface Gulf Stream, is the rotational coupling that holds the conveyor in its operating mode. When the pin loosens, the system drifts inside the operating mode. When the pin fails, the system snaps to the other mode. The other mode is what the geological record calls the younger Dryas. And the only known way to leave the other mode is to wait, possibly for 1,000 years, possibly forever. There is one more aspect of the younger Dryas record that I want to mention briefly, because it is the part that most directly connects the ancient collapse to the modern situation. The younger Dryas was triggered by a single, relatively brief freshwater pulse. A glacial lake gave way. The water spread. The conveyor shut down. The system entered the not running mode and stayed there for 1,300 years until the forcing relaxed and the system snapped back. Today, we are not delivering a single brief pulse. We are delivering a continuous, accelerating flow. Greenland is not a finite glacial lake that drained once and then was empty. Greenland is a continent-sized ice sheet that contains approximately 7 meters of sea level equivalent fresh water, and it is currently losing mass faster than at any point in human history, with the loss rate trending upward, not downward. The younger Dryas trigger was a moment. The modern trigger is a sustained process. Whether the modern process delivers fresh water into the same critical region of the North Atlantic at a rate sufficient to push the system over the bistability ridge is the question the Utrecht study cannot yet fully answer. What it can say is that the response is already underway. The first stage of the response is observable in 3 decades of satellite data. Whether the second stage arrives depends on the integral of Greenland melt over the next several decades, on the response of the deep current to that melt, on whatever feedbacks dampen or amplify the system, and on the simple, unknowable question of how far into stage 1 we already are. The geological record offers us one piece of guidance. The last time this happened, the world that emerged on the other side was not a slightly different version of the world that went in. It was a tundra version, with a frozen Britain, with glaciers expanding, with a 1,000-year wait before things returned to something the surviving populations could call normal. The Utrecht study did not arrive in a vacuum. It is the latest entry in a body of research that has been building for years. 4 studies in particular, all published in major peer-reviewed journals, all converging on the same direction, all signaling the same general thing, even though each one approached the AMOC from a different angle. In 2021, Levke Caesar and her colleagues published a paper in Nature Geoscience titled Current Atlantic Meridional Overturning Circulation, Weakest in Last Millennium. The team used a multi-proxy approach: tree rings, ice cores, ocean sediments, coral records, historical ship logs. Each proxy is a noisy, imperfect record of past ocean conditions. But when you combine 11 different proxies into a single picture, the noise tends to cancel and the signal sharpens. The result placed the current AMOC at the weakest state it has been in for at least 1,600 years. 9 of the 11 datasets showed the 20th century weakening at statistically significant levels. The signal is not just below the median of the past 1,000 years. It is outside the envelope of normal natural variability across the entire Common Era. The Atlantic has weakened to a state that, as far as we can reconstruct, it has never been in for the entire span of recorded civilization. Also in 2021, Nicholas Boers at the Potsdam Institute for Climate Impact Research published observation-based early warning signals for a collapse of the Atlantic meridional overturning circulation in Nature Climate Change. The Boers study took a different approach. Instead of asking how weak the AMOC is, it asked whether the system was showing the statistical fingerprints of approaching a tipping point. Tipping points have a recognizable signature in the data. Systems near a tipping point lose their ability to recover from small perturbations. They become slower to return to equilibrium. Their variance increases. Their autocorrelation lengthens. There are 8 independent statistical indices that can detect those fingerprints. Boers applied all 8 of them to the AMOC observational record. Every single one of the 8 indices showed the same thing: loss of dynamical stability. The AMOC, by every statistical measure of system stability you can apply, is no longer the same kind of system it was 60 years ago. It is wobbling. Boers, who is generally a careful scientist, called the trajectory worrying as well as surprising. In April of 2026, just last month, a team led by Portman and colleagues published Observational Constraints Project, a 50% AMOC weakening by the end of this century in Science Advances. The Portman team used a statistical method called ridge-regularized linear regression, which is uncommon in climate science but well established in machine learning. The method takes a large ensemble of climate models, scores each model against 19 independent real-world ocean measurements, and weights the ensemble according to which models actually match what we observe. The result narrowed the predictive uncertainty by approximately 60% compared to the standard ensemble average, and it produced a 51% weakening estimate by the year 2100. The previous IPCC consensus had been around 32%. The new estimate is about 60% worse. One of the biggest sources of the gap, the Portman team found, was a long-standing bias in the South Atlantic surface salinity that previous models had not corrected for. Correcting that single bias accounted for 47% of the difference between the old projection and the new one. And then there is Stefan Rahmstorf. Rahmstorf has studied the AMOC at the Potsdam Institute for over 35 years. He is, by any reasonable accounting, one of the senior figures in the field. Earlier in his career, Rahmstorf estimated the probability of full AMOC collapse this century at approximately 5%. He has revised that estimate, publicly, recently, to greater than 50%. He has called the situation the most dramatic climate changes in 100,000 years. He has stated that the point of no return, the threshold past which AMOC collapse becomes inevitable regardless of any subsequent emissions changes, could be reached as early as the middle of this century. And he has been explicit that current climate models likely underestimate the speed of weakening because most of them do not incorporate Greenland meltwater into their forcing scenarios. Caesar showed us how weak the AMOC is. Boers showed us how unstable. Portman showed us how fast the weakening is likely to continue. Rahmstorf showed us how dramatically the field's own assessment has shifted. What the Utrecht study added to that body of evidence is the piece that was missing: the mechanism, the reason all of those weakening signals are tied together physically. The deep western boundary current pin is what unifies Caesar's paleoclimate signal, Bohr's statistical instability, Portman's projected slowdown, and Rahmstorf's revised risk estimate into a single coherent picture. Each of those studies was independently telling us something was wrong. The Utrecht study tells us what mechanism that something works through. And the model now lets us watch the mechanism in real time, using satellite data we have already been collecting for 30 years. So what happens if stage 2 arrives? The consequences are not speculative, and the Utrecht result does not change them. It only sharpens the timeline. European average winter temperatures drop by approximately 10 degrees Celsius. London faces winter lows near -20 Celsius. Scandinavia becomes tundra, colder than modern Siberia. Northern European agriculture, which has been built around relatively mild winters and reliable growing seasons for centuries, simply stops working at scale. The food supply chains that depend on it stop too. Sea ice, currently confined to the Arctic, creeps southward and swallows coastlines in Britain, in Iceland, in Norway. Ports freeze that have not frozen in 1,000 years. As the North Atlantic cools, the great tropical rain belts shift. The monsoon systems that supply seasonal rainfall to West Africa, to South Asia, weaken and drift southward. The food supply for more than 1 billion people is disrupted. The AMOC also drives the upwelling of cold, nutrient-rich water from the deep ocean to the surface in the Atlantic and elsewhere. Without that upwelling, surface waters are starved of the nutrients that feed phytoplankton, which are the base of the entire marine food web. Every food chain that depends on the ocean collapses behind the base of the chain. These are not the only consequences. Sea level along the United States East Coast rises by an additional 50 to 100 centimeters as the Gulf Stream's offshore push weakens, on top of any thermal expansion or ice sheet contributions. Atlantic hurricane behavior changes as the redistribution of ocean heat alters where and how cyclones spin up. The El Nino Southern Oscillation in the Pacific is amplified by approximately 11% through teleconnections to the weakened Atlantic. The system that the AMOC stabilizes is not just Northern Europe. It is the entire Northern Hemisphere climate system. Now, with all of that on the table, let me dispatch the predictable alternative claims briefly, because they will appear in the comments of every video on this topic, and they deserve clean answers. Someone will say that the current AMOC weakening is just a natural cycle. The Atlantic multi-decadal oscillation, they will say. Or some other natural oscillation. Caesar, 2021, disposes of that one in a single number, 1,600 years. The current state is outside the envelope of natural variability across the entire Common Era. Natural oscillations operate on timescales of years to decades, with amplitudes that fit inside that envelope. This signal does not. Someone will say the weakening is just measurement noise from the rapid array. The Utrecht result disposes of that one. The 53-kilometer drift is observed in two independent data streams that have nothing to do with the rapid moorings. Satellite altimetry, subsurface temperature, 3 different observational systems using 3 different physical principles, all showing the same thing. Someone will say geoengineering or weather modification is responsible. The energy budget disposes of that one. The AMOC transports 1 petawatt of thermal energy continuously. 1 petawatt is many orders of magnitude beyond any deployed or plausible weather modification technology. The largest known geoengineering proposals operate on energy budgets that are roughly 10 orders of magnitude smaller than what would be required to push the AMOC into stage 1. The forcings that are driving the weakening are direct, measured, and well understood. Greenland melt, surface warming. They do not need a covert technological program to explain them. The simpler and well-supported explanation is sufficient. And someone will say that there is a cover-up, that scientists are hiding the truth. Here is the actual answer to that one. The Utrecht paper is openly published. The Caesar paper is openly published. The Boers paper is openly published. The Portman paper is openly published. Rahmstorff's revised risk estimate is on the record in interviews and public statements. There is no suppression. What is true, and what is worth examining honestly, is that mainstream news ecosystems are structurally bad at communicating slow-moving climate threats. The AMOC story does not produce a discrete, photogenic, single-day disaster. It produces a decade-scale signal that does not generate headlines. That is a structural problem with how news is made. It is not the same thing as a cover-up, and it is the part of the younger Dryas record that should worry you most. Civilizations do not usually fail by missing dramatic warnings. They fail by normalizing slow signals until those signals turn into something that cannot be missed. So what should you watch? 2 things. and they are both watchable, both publicly available, both updating continuously. The first is the Gulf Stream drift rate itself. The Utrecht study gave the field a satellite observable signature. The satellites are still flying. The data is still being collected. The drift can be tracked. And the most important thing to watch is not whether it continues. It will continue. The most important thing to watch is whether it accelerates. Stage 1 in the model is a slow drift. Stage 2 begins when the drift rate increases. The transition between them is the inflection point. A measurable change in the rate would be the first observational warning that the pin is about to fail. The second thing to watch is Greenland. The faster Greenland melts, the more freshwater forcing accumulates, and the faster the AMOC response. Continued acceleration of Greenland ice loss would compress the timeline. A slowdown would extend it. The GRACE follow-on mission is still in orbit, still measuring. Those numbers are also public. The Utrecht model's 25-year window from end of stage 1 to full collapse is, again, a model output under idealized forcing. The real-world figure could be substantially different. What the study delivers is not a countdown clock. It is a mechanism, a satellite observable signature, and a confirmation that the signature is already present in real data. The first stage of the most important ocean current on the planet is no longer a hypothetical. It is a measurement. For 31 years, the signal was sitting in publicly available satellite data, waiting to be read. The Gulf Stream was drifting. The data was there. Until a Dutch supercomputer ran for 6 months at 10-kilometer resolution and identified the underlying mechanism, no one could read what the drift meant. Once the mechanism was identified, the meaning was obvious. We are inside stage 1. We have been inside stage 1 by the available evidence for at least the 31 years that satellite altimetry has been continuously available, and probably longer. The question the field cannot yet answer is the only one that finally matters. We know we are in stage 1. We do not know how deep into it we are. Whether we are at the start, the middle, or near the end of the long, slow drift that ends in a 2-year hinge and a younger Dryas. The drift rate, watched patiently, watched honestly, watched without flinching, is the only way to find out. And the part of all of this that should follow you out of this video is not the model, not the 400 years, not the 25-year window, not even the 53 kilometers. The part that should follow you out is the structural lesson buried at the bottom of all of it. The signal was there for 30 years. The data was on public servers. The satellites were in orbit. We were not blind to the data. We were blind to the mechanism. Once the mechanism arrived, the signal became unmistakable. The next mechanism, whatever it is, whatever system it describes, is probably already in our data too. We are just not yet equipped to read it. The first stage of the Atlantic conveyor's collapse is a measurement. It is sitting in the satellite record. It is waiting. The thing about a measurement is that it does not care whether anyone is reading it. The satellites will keep flying. The altimeters will keep recording. The drift, whatever it turns out to be doing over the next several years, will be there in the data, whether we look at it daily, weekly, monthly, or never. The work the Utrecht team did was to attach a name to the drift. The work that comes next, the work that researchers in oceanography labs across the world are now beginning, is to watch the rate, to plot it, to see whether the line stays roughly straight, the way stage 1 says it should, or whether the line starts to bend upward. A small upward bend is what a loosening pin looks like in the seconds before it lets go. A large upward bend is what comes after. There will be people who say, throughout the years it takes to track this, that nothing is happening, that the doom never arrived, that the headlines were overblown. They will be technically correct in the same way that someone is technically correct when they say the dam is fine, right up until the water starts spilling over the lip. Stage 1 is, by design, undramatic. That is what makes it dangerous. It is the part of the trajectory that looks like nothing until the moment it does not. And the people watching the data closely will see the rate change first. By the time the rate change is visible to anyone who is not watching the data closely, the system is already in the hinge. The honest summary of where we are, as of the date of this video, is this: the Atlantic conveyor, the system that has kept Europe habitable, that has anchored the northern hemisphere climate, that has fed the surface ocean nutrients that feed the bottom of every marine food chain on the planet, has been weakening for at least a century. We can see the weakening in tree rings and ice cores stretching back 1,600 years. We can see the weakening in observed flow rates measured by moored sensors at 26 degrees north. We can see the statistical instability of the system in 8 independent indices. We can see the projected slowdown in models constrained by observations. We can see one of the senior figures in the field revising his personal risk estimate from 5% to over 50%. And now, as of 2026, we can see the physical mechanism, the deep current pin that ties all of that together into a single coherent picture. The first stage of the most important ocean current on the planet is no longer a hypothetical. It is a measurement. It has been a measurement for 31 years. We will be tracking this as it develops.